Good morning. Sorry for the delay. Good morning. Good morning. Good morning. Good morning. Wait, can you actually hear me? Yes. Okay. Good morning. We're going to start. Good morning. Good morning. I'm not even saying names. Why am I not saying? Okay. Good. Oh, it doesn't give. Okay, wait. This doesn't even. Okay. I'm going to go to the chat first, actually. Good morning, Good morning, Luani. Good morning, Munera. Good morning, Monpreet. Good morning, Sarah. Good morning, Pushpita. Good morning, Sydney. Good morning, DJ. Good morning, Tree. Hold on. Good morning, Monpreet. Did I already say that? Good morning, DJ for the double. Pushpita. Munera for the double. Sarah. Good morning, Eric. Kayla. Good morning. Okay, this is already confusing. All right, let's just get rolling. I'm gonna um Yes. All right. This is confusing. All right. Good morning, Eric. Good morning. Who else didn't I say? I think that's everybody. Okay. Let's actually get rolling. And good morning, DJ and Tree and Sydney for the double, triple hat tricks. Okay. I'm just going to get rolling. I don't have your exams yet. They are in progress though. They're not going to take forever. They're not going to take forever, but they are going to take a little bit more time. I'm hoping to have them all to all sections by the end of the week. I don't want to jinx myself, but and I'm hoping to just get them all done by the end of the week and release them all at the same time. So that's why I'm holding off for a little bit until I finish all of them. But if I start falling behind and it starts getting too ridiculous, then I'll just release them as I go. So I'm just saying. So I don't have them yet. I apologize, but they are coming. So that said, wait, and you are Tuesday, so you had lab Thursday. So yes, I heard about lab Thursday already. Right. All right. So I just want to get straight to this homework that you're in the middle of, the homework that the board meeting took you somewhat through. The board meeting took you through the first five exercises. Hold on. The lab meeting took you through the first five exercises about electrostatic force between one source charge and one test charge. And then the test charge kept changing its magnitude. Nothing else changed. That's up. Some practicing those exercises over and over in the board meeting is partially meant to start to get you to see why we call the test charge the test charge. Good morning, Alice. Awesome. Um, right? It sort of puts more emphasis on the source. The source sits there and is fixed. It sits there at a certain distance from a particular location in space, and then in space we keep testing different receivers for the effect of that electrostatic force coming from a certain amount of fixed source charge that's a certain fixed location, right? So that's what you did or discussed in the board meeting last Thursday, and you got answers to it and all that, right? But then, so I'm summarizing now. Well, again, I'm saying that then there was more to that homework packet that you're working on right now. There's a third page that's a lot more involved computationally. That's what you're working on right now. Hold on, I'm just looking. Um, and that's what I want to get to right now. To be totally blunt, my goal by the end of today is to actually get you the answers to the end of that homework that evidently is due Thursday, not due today, right? So if you stay with me today mentally, I should have the answers for you. So your homework uh, for Thursday is a thick computation. I mean, it's not short, but actually, and I would like you, of course, to hand it thoroughly with the 5-step method and all that kind of stuff. But to be clear, again, I'm sort of going to lay it all out for you today. So your job in this case is sort of a more traditional science job. You're just going to show fully that you get it and work it all out. But I'm going to do it for you right now, or try. So okay, so that's what's happening. This is the old, I'm using the old PDF. I'm gonna flip to the relevant pages where we started to set this up in the old PDF, and then I'm gonna continue. Well, yeah, maybe I'll do that right now. All right, well, I guess I want to say this front page right here now. This page may have been up last week. It may have been a little abstract last week, but now let me say what this front page means. One conclusion that you were being guided toward in the board meeting on Thursday was that if you, yeah, I'm gonna switch screens for a second to show you what I'm about to say. Bear with me for a second. So I'm gonna remind you of what you did on Thursday. Here we go. Hold on. Okay. Yes. Okay. Okay. So here it is. Right. Okay. So this, what you're looking at right now, is what you did on Thursday in the board meeting. Now, let me say something. So you got some answers, right? And again, I believe the answer to the first one was approximately, hold on, and you should correct me or you should check. You should have this in check if I'm wrong. But the first one was like 1 times 10 to the 10th times 50 times 3, so 150 over 25 is 6. Right. So the first one should have been approximately 6 times 10 to the 10th newtons. Someone should really confirm or deny in the private chat if that is a familiar answer for exercise 1. From the board meeting on Thursday. I believe it is. Now I'm rounding up sort of substantially. I'm saying approximately 6 times 10 to the 10th newtons. In other words, like 60 billion newtons would be the answer to the first one. If you did the calculation a little bit more exactly, you would get something like 5.91 or 5.97. I can't remember, but 5.9 something times 10 to the 10th newtons for the exercise for the first one. Can anybody actually confirm or deny in the chat, in any kind of chat, whether that answer sounds familiar for the first exercise sitting right here on the page? I'm saying, okay, I would love some recognition that I'm talking even. Someone's here. I think and again, you've already done this. I don't want to get bogged down in the plug and the chug, but something in the chat. And I see a thumbs up. Thank you for the 5.4. Okay, great. Fine. So you got like 5.4. And as I say, I'm rounding substantially. I rounded in my mind. I just did it so I could do it in my head. I rounded 8.99 times 10 to the 9th to all the way up to 1 times 10 to the 10th. I mean, that's a big round. So, okay, you got 5.4 times 10 to the 10th. Great. Now that sounds more accurate. Sounds terrific. Okay. And that is just literally multiplying K times K times K. Excuse me. I know it's not. It's multiplying K times capital Q1 times lowercase q2, dividing all by R squared. All right, so we'll go with 5.4 times 10 to the 10th for the first one. Thank you. And you should give yourself points for that, people who just responded. Now, here's my point. I'm not here to plug in again for you. You spend an hour and a half plugging in. What I'm here to say is, okay, then we get to the second exercise, and we could plug in all again to get the next force, right? We could plug in all again, and we would get the correct answer if we did. But many of us might have noticed, or perhaps you discussed with Professor Cologne or whatever, that in fact, since the only thing that changed from exercise 1 to exercise 2 And the reason that we call it, the only thing that changed was the charge that's receiving this force, right? And then again, this is sort of why we call that charge the test charge, because we're kind of testing what the different results will be depending on doing nothing but changing its magnitude. So we swapped out the 3 coulomb from this little chamber over here at 5 meters from a 50 positive coulomb. We swapped out the positive 3 coulomb and we put in a -6. Like we put in twice as many little particles, except there were now electrons instead of protons. So some of us might have realized, well, if that's the only thing that we're changing in this equation, if that's the only thing, where's my tools? If that is the if this is the only thing that we're changing in all of this, then really we should only have to adjust by that amount to get our new answer. In other words, F, the magnitude of F, is directly proportional to the magnitude of Q2 as long as everything else stays the same, which it does in this case. So many of us might have realized, oh, okay. Wait, that's inconvenient. So many of us might have realized, okay, all you got to do is take your old answer, 5.4 times 10 to the 10th, and multiply it by -2 and get a new answer, like 1.1 times, excuse me, -1.1 times 10 to the 10th newtons, right? And again, please note, I'm trying to make a point here, ultimately. Note that my answers to what I'm saying right now are all in newtons. Right now, we're calculating forces, right? What one object is doing to another object. So the answer to the second one, you might be able to get somewhat easily by simply taking your answer from the first one and multiplying it by -2. That is not cheating. That's a perfectly legitimate insight, right? So it saves you time and you get an answer. But then, if you're like me, you then get to the number 3 and you say, okay, I could do that trick again if I want. Like, why not? Except that now number 3, the multiplication isn't so easy anymore. Like now you would have to like multiply by -6/5 or something to, right? Because you're now like doing that. You're like changing it by a factor of 6/5 or 5/6 or whatever. Well, that you could still do that, but that's somehow not as pleasant. You can't really do it in your head as what you did before. So some people might do it and some people might not, right? I'm just observing. I'm trying to make a point here. I'm observing that going from 1 to 2, there's kind of a trick to do it. Going from 2 to 3, there's still a trick, but it's like not as satisfying, really, possibly. Then you go, so you do whatever you do. Then you go from 3 to 4. Okay, and now maybe you sort of divide by 5, right? And you get the answer to 4, which, by the way, I think is probably like 1.8 times 10 to the 10th newtons, right? Positive 1.8 times 10 to the 10th newtons. How do I know that? Because what I might have done, what you might have done is I might say, these numbers are getting annoying, but I have the original answer. So to get from the original answer of using +3 to +1, I could just divide my original answer by 3. So that's what I just did in my head, right? And now you get, here's the point of all this madness. You get to exercise 5. And what you might realize, or you might understand right now as I'm telling you, is by the time you get to exercise 5, then you look up and you're like, wait, I have the answer to 4. The answer to 4, and again, you guys should be, after all the time we spent just plugging these in, if you have the answers with you, you should be following along and making sure you agree with my answers. By the time you get to number 4, I think the answer is like 1.8, positive 1.8 times 10 to the 10th newtons. By the time you get to number 5, then you can say, aha, you can say two things. You can say, number 1, I'm just going to take my answer for 4 and multiply it by -2 to get my new answer. So I think my answer to number 5 is -3.6 times 10 to the 10th newtons. right? That's insight number one, that you could, now the trick, is sort of satisfying again. You can just take your answer for number four and multiply it by -2. But furthermore, you might have some kind of reaction of going, oh, for heaven's sake, like, why didn't Yaverbam just ask me that from the get-go? You might even, in other words, you might have that weird moment that often happens in physics where this moment something clicks together and makes sense or seems like you have a right answer. You might then, I'm not saying you should, but it would be very common if right after getting a right answer or seeing that something makes sense, if right after that you go, oh, God, that's like so straightforward. Like, eat, and then either go, oh, I'm an idiot. Why didn't I see that before? That's what I do. Or go, oh, what a jerk he is. Why didn't he show me that before? Like, you might get angry at yourself or angry at someone else. I'm not kidding here. There's something weird about physics. And I swear, famous Nobel Prize winning physicist Richard Feynman pointed this out also in a book, an autobiography, like a long time ago, where there's something about physics where for a while it doesn't make any sense. It doesn't make any sense. It all seems absurd. It seems like stupid and annoying and crazy. And then the minute we get something in physics, instead of being like, yes, 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 for like a long time and being like, I'm so smart, or whatever, or the universe makes so much sense, the universe makes so much sense, we very quickly go like, oh, that's so stupid. Like, duh. Like, why didn't anybody just point this out before? Or why didn't I see this before? Like, you get angry at somebody, right? First of all, let's try to not do that. It's really tempting, but really, when you get something right, like actually just dwell in the joy of it rather than moving straight to anger about it. But more to the point here, what I'm saying is yes. By the time you get to the fifth answer, you might realize that if only we had asked you the fourth question first, or if only you had noticed the fourth question first, if only the fourth question had been asked or answered first, then all the rest would have been a lot easier. I'm seriously saying this. This is a real point. It is not off the topic. It is the topic. That 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 fourth question that's asking what would be the force if this particular amount of source charge at this particular location, what would be the force that it would exert onto a +1 coulomb of test charge? Or in other words, what would the force be if a bunch of source charge fixed and given a, a, pulled or pushed a positive unit charge at a certain fixed distance? If we would get that answer, the answer to number four, in this case, the 1.8 times 10 to the 10th newtons, if we knew what this 50 coulomb source charge were doing to each unit positive charge at a given distance away, then from then on, we would know what would happen to anything that might or might not, any amount of positive or negative charge that might or might not land or be found at that fixed distance away from the source charge. In other words, the answer, and I know it says this on the sheet, but I cannot emphasize this enough. The question of number four, it looks sort of innocuous and sort of hidden there until you're grinding through all this. And then you start seeing how significant really number four really is. It's the answer that really makes all the other answers a lot easier. So the answer to number four, we could call the force per charge, right? It would be the amount of force that this source would exert per every 1 bit, 1 unit of positive charge that could ever be at a specific distance from it. That force per charge is so calculationally important and turns out to be so conceptually important that we could call it force per charge, or we can make a new word for it because we're going to use it so much and call it the field. Okay, Now, again, I mean, it says it right here. Hold on. It says it right here, and it's meant to be the takeaway from the board meeting, but I'm trying to emphasize right now, because from now on, the rest of this course is about a very unthingy, immaterial notion known as the field. From now on, we're all about fields in this course. So I want to be very clear. I want to be very clear that we're transitioning now, that we're moving from a notion of forces to a notion of fields. Computationally, it is at this moment, a straightforward step. Field just means force per charge. If the force is something that one charge does to another charge, the field is something that one charge just does. Like I'm saying, mathematically, the force is Q1 times Q2 over R squared. The force regarding point charges, point sources. So the force is Q1 times Q2 over R squared. That's the force that Q1 exerts on Q2. The field that is exerted by capital Q1 is all of what I just said divided by Q2. It is simply KQ1 over R squared. And once there's only one Q in there, you don't really have to put the one in anymore. So the force, I'm going to say it again. I'm going to move on because all of a sudden now we're going to get into a computation that actually is kind of thick. So it's hard to hold on to the forest for the trees sometimes until you get used to it. So what I'm trying to say very explicitly now, there's no trick up my sleeve right now. If you want to know the difference between force and field, mathematically or computationally, the difference is literally that force is between two objects and field is what is done by one object. Force is KQQ over R squared. Field is KQ over R squared. Field is, now a little bit more conceptually now then, field well, conceptually what I'm saying, and I'm going to move on, is we used to say like proton pulls electron, right? Or proton pushes other proton, like that would be a force. Proton is here. There's another proton over there. So the first proton pushes the second proton. That's force. Now what we're going to start to say is first proton is here. It makes a field over there at that point in space. In fact, it makes a field vector at every point in space. The minute a proton exists, it allows the universe to know how big it is and at where it is by placing a vector at every single point in space, a different vector of a different size and a different orientation at every point in space. At every point in space, that vector that's sitting there is a prediction of how hard this source would push or pull onto any and every 1 coulomb of positive test charge that could be at that given location in space. So a proton makes a field. It exerts newtons per coulomb everywhere in space. And then when any coulombs come along to those points in space, they feel a force from the field. So we used to say proton pushes proton. Now we say proton makes field. Other proton lands in field. Field exerts force on other proton. There's an intermediate immaterial agent now known as the field. What is the field? It is the force waiting to happen. The force per charge. So field is force per charge. Force is field times charge. And field is and I'm going to turn the page now. Mathematically, what the field do to a source charge is a vector valued function. It is a bunch of vectors everywhere in space, a pattern of vectors everywhere in space due to a source. And each of those vectors says, oh, good. Okay, I'll get you in 1 second. Awesome. Each of those vectors says how many newtons will be exerted per every positive coulomb that could or would or will ever land at that point in space. So force is newtons, field is newtons per coulomb. Okay, Alice, yes. I think you're on mute. Yeah, okay.
Yeah. So is Q1 like the field and then Q2 is the other proton, or is E the field?
Great question. E is the field. Q1 is the thing that's making the field. Q1 is the reason that the field exists. Like E is the field. So yeah, so Q1 is the original first proton, the source or electron or a bunch or whatever. But yeah, Q, capital Q is the bunch of charge that the minute it exists, it's creating a field everywhere called E. And E is is a vector, like is a different vector at every point in space, and the vector is calculated by Q by the Q1 divided by the distance squared, all multiplied by that universal constant. Does that, I mean, that's a great question. Does that make sense? Does that answer make sense?
Yeah, thank you.
Okay, thank you. Awesome. All right, and that's points. All right, and that's a perfect segue. That makes me feel like something is concrete somewhere. So I'm going to now switch this. So I'm going to do now. Okay, well, so I always say, so we're going to do this now. Like, and I know I already set it up, started setting it up for you last week. Like, I you know, I don't want to wrap it all. My goal in the next 47 minutes is to like literally get to an answer for this. So like I'll get going, but like what's going to happen now here? See, now we have this notion of field. Again, field is a when I say it really is a field, by the way. I mean like whenever you picture field, what do you picture? Like what am I saying? You picture a bunch of arrows in space, pattern of arrows in space. Like that is what you picture to picture the field. And we're saying that every single object that exists in the world makes its own pattern of arrows in space. Every single object, like a proton over here makes a field, then another proton like over here makes a bunch of arrows, right? And another one over here, blah, blah. And then anywhere that you ever go in space, you experience the sum total of all of these contributing arrows, right? I mean, you know, it's just like saying, it is literally like saying, like, you know, in outer space, like the sun is in outer space. So it's pulling everywhere gravitationally toward it, right? Um, but then also, like Jupiter is in outer space. It's pulling everywhere gravitationally toward it. Not as much as the sun because it's like not as heavy, but it's making arrows that are coming toward Jupiter everywhere in space. So then you come along, and so is, you know, Uranus and everything else, and other stars and all that, right? But then you come along and you're Earth. So you come to some location in outer space. There's already an arrow there pulling toward sun. But then there's another arrow there pulling toward Jupiter. Now the arrow toward Jupiter is probably is a smaller arrow, like unless you're like right near Jupiter. But all other things being equal, there you got these two different arrows, one pulling toward the sun, one pulling toward Jupiter. So, and let's assume for the moment like that everything else is so small or so far away that they're making arrows that are not as big. I'm just saying as the suns and so if you're Earth and you go to this like location, you land at this location, there's an arrow already there pulling toward the sun, a field contribution from the sun, and there's a field contribution from Jupiter. So what happens to you if you're Earth? You get pulled in a certain direction in a certain amount that is the vector sum of those two contributions. Truly, honestly, the vector sum of a whole bunch of contributions, but maybe a lot of the other ones are so small that they don't make that big of a difference. Well, this problem that we're about to do right now is that in this problem, in this setup, we're now just talking about charges instead of masses, but we go to the Cartesian plane in the lab, and we assume, we believe, okay, so here well, yeah, so I'm going to switch. Oh, and there's something in the chat. I'm sorry. Hold on. And I'm going to, oh, okay. I'm looking. So someone's checking the answers in the chat, which is great. And if I missed it a long time ago, oh no, it was 2 minutes ago. Okay. Yeah. The answers are yes. I'm just looking at the answers. They look right. Yes. I know what you're talking Oh yeah, no. Okay, okay. That was a very polite question, and you should give yourself a point. So someone was checking their answers in the chat, and I do agree with the answers, and that's awesome. And thank you. No, that's good. Like that's what we should be doing. But then they also asked in the private chat a good. They're also confirming if you in all those answers from the lab or and from now on, if you get a negative answer, is it true that that means attraction? And whereas if you get a positive answer, that means repulsion. That person's asking that. It's a very direct, good question. I am saying explicitly, yes, that is correct. You get it. I'm psyched. Positive means repulsion, negative means attraction. Yeah, and that's going to continue to be true. Yay. Yeah, that's awesome. Yes. Okay. That's going to continue to be like true in what we're going to do right now. So that's another perfect segue for me to switch the pages and get to the work of this. If I can. Hello. Wait. Hello. Okay. 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 Right. Okay. So this page right now just literally says everything I've just been saying for 15 minutes. The field is force, is net electrostatic force per charge. So it's the prediction of what any one source would do to um, to unit charges at various locations, right? So now I'm just skipping. Okay, so then we get to this homework thing here. Okay, so the homework asks the question, what if more than one source charge acts on, now I should really say now that we're talking about field, on one right? We're now going to look at. So now we've developed now the idea of field, which is force per charge, where we're saying field is a vector. It has magnitude and direction. So and we're saying field is this idea that at any point in space you are, there's a vector sitting there saying how hard and in what direction you'd be pulled or pushed if you were a 1 coulomb positive charge. So now I'm saying the homework is saying, okay, fine. So if I want to know the field, like right here at this spot, at the origin of some coordinate system, what if there's more than one thing going on in the world? What if there's a bunch of charge, source charge over there, and there's a bunch of source charge over there? What's the field here? So that's what we're about to answer. To be clear, then, I'm now saying that this confuses people sometimes, what I'm about to say. I'm saying, in effect, what if there's more than one capital Q1? I'm not now saying like Q1, Q2. I mean, I'm not going back to capital letter, lowercase letter. I'm saying, what if there's a big Q over here causing a field vector over there, but also there's a completely separate big old capital Q over here causing its own field vector over there? Like what then what's going on over there? So I'm not, well, so I'm going to draw a picture of that. I'm going to try to find the field at the origin of a coordinate system. I'm really going to place the origin of a coordinate system at the location that I'm interested in knowing the field. I'm going to try to find the field at the point 0, 0. Let me emphasize, there's nothing, I've just placed my coordinate system there. I'm just looking at a certain place. I call it the location of interest. Websites and ChatGPT and all that kind of stuff will often call this location the field point, the point at which we're calculating the field. I'm going to tell you right now, I don't love that phrase. It confuses me because it kind of makes it sound like there's this special point that has field at it. I'm saying there's field everywhere, and we're just looking at a particular arbitrary representative location to find the field. The field due to Q1 over here and Q2 over here. So here's going to be the example. I see there's something in the chat. I'm psyched. I will take a breath. I'm going to just quickly say, so here, and I know you've seen this picture before, but this is my step one DFP. It's a little crowded. It's a little busy, but it's my step one DFP of of the homework situation. Let me just adjust it right now. I'm going to get the chat. Hold on one sec. And I'm going to explain all this, obviously. Um, uh, Hold on one. I'm totally going to get the chat in one. I just want to make this absolute. Okay. Yes. This is my step one DFP. I'm going to explain in a second. Let me just look at the chat. Okay. Oh, okay. Actually, that's a very good question. I'm relieved. I was a little nervous there for a second. Very good question in the direct chat. Okay, so I'm going to ask it out loud. Okay, but let me say the situation so the question will make sense to everybody. Like, so this is a picture of the sheet, that was just screen shared a moment ago, like your homework sheet. In this situation, you've got this strong Q1, this positive 5 coulombs, which really means like 80 quintillion protons are jammed together in this small spot at the coordinates positive 5 comma positive 4, right? That's what the white Q1 is over there. It's this strong charge that's sitting there, in the first quadrant. Then you've got this other charge Q2 that's sitting way out there, also in the first quadrant at coordinates 10 comma 3. Now Q2 is weaker, and also it happens to be negative. So in other words, Q2, instead of being like 80 quintillion protons, it's more like 32 quintillion electrons jammed together over there. And I'm going to repeat, what we're now going to look at is what's the combined effects of Q1 and Q2 onto this arbitrary but representative location known as the origin, right? We're going to look at the combined effects of the two. In other words, and then I'm going to answer this chat question, which is very good. In other words, what we're not looking at, and this could, we are not looking at what Q1 is doing to Q2. It is doing something to Q2, but they're both held fixed in the lab. Like they're both in chambers, like sitting there, like held in place. So I don't care what Q1 is doing to Q2. That isn't the question. The question is, or the idea is that Q1 is creating field vectors everywhere. Q2 is creating its own field vectors everywhere. Any spot I look, the two field vectors from the two charges are being added together and making a resulting impact. That's what I'm looking at. Okay, I'm literally gonna add the two vectors that land at the origin. I'm gonna do all this computation to just add the two field vectors that land at the origin, and I'm going to get one big answer. So the person's question in the chat says, wouldn't the stronger of the two affect this problem? Like the sun pulls Earth, but also Mars also pulls Earth, but the sun has a greater pull than Mars. That is exactly correct. Of these two in this problem, Q1 is going to have a larger impact. It's going to then Q2 onto the origin. But it doesn't mean that Q2 has no impact. It's absolutely true. I mean, yes, that the answer we're going to get is going to be sort of like more similar to the kind of answer we would get if Q1 were the only game in town. But it's not going to be identical to that. The answer we're going to get is going to be somewhat affected by Q2. But you're right, not as much. But again, what I want to say, but it really is a deep and good question. Okay, well, I'll try to go back to that question in a second once I start talking about the actual vectors. But again, I want to make this is called superposition of forces or superposition of fields. Again, this is all Galileo, really, like below the surface, in the sense that what will happen at the origin is the sum of independent parts Q1 will make a vector that we call a field contribution, and Q2 will make a vector that we call a field contribution, and each contribution will exist as though the other contribution isn't there. Like it's like Q, and this is not a joke. It's not like Q1 is about to put a vector there and then like looks over at Q2 and goes, oh, wait, you're putting a vector there too? Maybe I won't put in so much. Like, no. Q1 makes an independent contribution, like places an arrow at the origin, and Q2 Q2 doesn't care that Q1 is there. Q2 makes an independent contribution, and then we add those together. So we say the whole is equal to the sum of its independent parts. There's no interaction between Q1 and Q2 that the universe notices. So even if Q2's contribution is smaller, it still makes a difference. Let me be more concrete now. But no, it is a great question. Let me be more concrete. I'm now saying, and I think I said this last week, and I'm looking at the time. Look at Q1, look at the picture. Q1 is this white dot, at coordinates 5, 4. If you imagine in your mind an R hat vector, if you imagine in your mind a 1 meter displacement arrow, like it's very subtle, it's in yellow here, like it's a very crowded diagram clearly, but if you imagine a little arrow of 1 meter length that points from Q1 to the origin, then imagine, so that's R hat 1, right? That sort of indicates the direct path, the direct direction from Q1 to the place we're looking at. Now you then scale up, you stretch that arrow by an amount, K Q1 over R1 squared. I'm going to do that math in a second, but just whatever those numbers are, you imagine now stretching that displacement arrow up by those amounts. So now it's a much longer arrow. And those amounts take into account units, like K has units of newtons meters squared over Coulomb squared. So the units change, and now you have this much longer arrow that's measured in newtons per Coulomb, right? It's like a force per charge arrow now. And you take this bigger arrow now and you place it at the origin, because the origin is where we're looking. You place the tail at the origin and the tip comes out from the origin, but you place it in that, you don't change its direction. You just move it over in that direction. So in other words, that's why the red line, the red arrow that is labeled capital E1, that red arrow is just a continuation on purpose of the direct line from Q1 to the origin. It sticks out along that line, and it says, okay, Q1 would push on the origin. Q1 would push on any positive unit of charge that could be on the origin, because Q1 is positive, right? It's all positive signs in here in my head. So there's a big old push at the origin from Q1, a big old contribution from Q1 that we call the E1 vector contribution. It's that big red arrow labeled E1. Now I go to the direct chat person's question and I go on in the problem. I say, okay, so there's one arrow there at the origin, but then we got Q2, same logic. Q2, I draw a line in my mind. I draw a little unit vector, R2 hat. From Q2 to the origin, it points to the origin. Then I scale up that arrow, but turn it into newtons per Coulomb and all that kind of stuff. But then I notice, wait a minute, when I'm scaling it up, when I'm multiplying by all the values, including Q2, I notice, wait, Q2 is negative. Q2 is negative. So that puts it a negative sign. So that arrow that was pointing from Q2 to the origin that I'm about to place on the origin, that would be another like push out from the origin, that has a negative sign in it. So it turns around the arrow, and the arrow points still along that line, but back toward Q2. So Q2 produces a pull on the origin, and that's the that's the red arrow labeled E2, right? I'm saying from Q1 there's a push at the origin, from Q2 there's a pull at the origin, and I noticed I made E2 smaller than E1 because it is the result of much smaller magnitudes. It's a much smaller charge Q2, right? In other words, it's a magnitude of 2 coulombs rather than 5. And Q2 is much farther away. The R in the denominator is a much bigger R. We're going to get to these numbers in a moment. So the E2 on the whole is a smaller arrow than the E1. But what I'm about to do, I'm going to turn the page and do the calculations. What I'm about to do is add those two vectors together, the E1 and the E2, and I'm going to get an answer. So in fact, well, yeah, so so if we treat Q1 and Q2 both as source charges, the question becomes, what's the net electrostatic field at the origin? So that's what we're trying to do. So we must compute the vector whose magnitude and direction tells us how hard and in what direction a positive 1 coulomb at the origin would get shoved by the combined effects of Q1 and Q2. Like that's what we're about to do. So the procedure is going to be that we add the vectors. We add the vector E1. So we have like a little free body diagram there at the origin. We've got an E1 coming out and an E2 coming out. The E1 is a big old push. The E2 is a small old pull. We're going to add them together ultimately by adding their components. But let me say, yes. But again, to the direct chat person in here, we're literally going to add this to this, right? So in our minds, if we're visualizing what's happening at the origin, we would place those two vectors tip to tail. Like I got a big thing going southwest and a small thing going northeast. If I were walking in New York City, if these were displacement vectors, it'd be like I'm walking this way and then I'm walking a little bit that way. So where do I end up? What's the result? The result is represented by an arrow that you could draw from the original tail to the final tip. That's the resultant field vector that we're looking for. This is a sketch of the answer we're looking for. And we are indeed looking for an arrow with a certain size and a certain direction. The colored arrow at the answer that we're ultimately looking for is Yikers Island is represented right here. Like that's the answer that we're looking for. I mean, it is the answer, but it just doesn't have any numbers on it. Literally, if we drew those arrows to scale, like with rulers and protractors and everything, then literally, however that final arrow would come out in a well-drawn diagram, if we just measured it and measured its angle, it would be the answer. So this is a long way. So I'm saying now, I'm going to start crunching the numbers. I keep saying that, but I'm going to start crunching the numbers. But I'm gonna know in my mind from advance that I should ultimately be getting an arrow that points pretty much to the southwest, because as the person in chat said, the southwest pointing vector here is like dominant. It's like enormous compared to the other one. So I'm going to get an answer that's pretty much going to point southwest if I do it right, just not as southwest as E1. Like it's going to be a little bit smaller than E1, my answer, if we check our numbers at the end. And the angle will be a little bit, well, the angle will be like, how can I say this? Well, in this diagram, it's not so clear, but the angle should be less steep and the magnitude should be less large, etc., because it's being affected somewhat by the other arrow. All right, I'll leave it at that. But our answer should be a southwest arrow, much like E1 is, because E1 is so much bigger than E2. It just won't be identical to E1 because E2 is having an impact on the situation. All right, so enough like overview. Let's crunch the numbers. How do we crunch the numbers? We zoom into each vector and we resolve it into its individual X and Y components, exactly as we, in principle, were practicing in Physics 203, like exactly as you would do with displacement vectors or velocity vectors or anything. So I'm going to zoom in. And in fact, now, so I'm going to start putting in numbers. So I'm going to zoom. So I'm zooming in. I just want to see something cool. Yeah, I mean, so I said this all abstractly last time. But I'm actually going to do it now. So, well, actually, I shouldn't erase it. Yeah. Okay, so this is a zoom in on E1, right? E1 is going southwest. It is therefore going some amount west and some amount south at some angle theta 1. Like that is E1. It can be resolved into two components, E1x and E2y. Um, I know I just erased this, but it's okay. You should stop me if those statements don't make sense. Like that's like from old physics in effect. So I want to plug in the numbers. So first of all, what do I mean by E1? Like E1 is the magnitude of the hypothesis. Oh, and I want to say very clear, everything I'm going to do now, like I'm going to, every time I draw arrows or triangles, I'm drawing them very deliberately with tips and tails in very specific places. Like the tips and tails are there to explicitly indicate direction, like not just sort of roughly. I mean, they are not guesses, they are explicit indications of directions. So the arrowheads take into account directions. Therefore, every computation I'm going to do now about the sides of these triangles um, is all about sizes. So, in other words, what I'm trying to say is that when I'm got every computation I'm going to do now is all just about raw magnitudes. I'm not going to take into account negative or positive signs because all the arrowheads will do that work for me. Okay, so what is the size of E1? The size of E1 is 8.99 times 10 to the ninth newtons meters coulomb newton meter squared coulomb squared times what? Times, okay, well, I'm going to do this on another page so it doesn't get so squeezed. Sorry, that's correct, but I just don't want to squeeze it. Sorry, so I'm going to start a new page. Sizes. E1 literally equals K, or what we call 1 over 4 pi epsilon naught times Q1 over R1 squared. That's the size. So what is that? That is approximately 9 times, I'm rounding, 9 times 10 to the ninth meters squared over a coulomb squared. Q1 is 5 coulombs all over R1 squared. What is R1 squared? R1. Now you want to track, make sure you R is 5 squared plus 4 squared. Well, I'll be more specific. 5 meters squared plus 4 meters squared. You should stop me if you don't know where I got that from. Where did I get that? Where did I get the 5 and the 4? I got it from the picture. This picture, right? Q1 is, I guess I'll draw it. I'm looking at the time. Yeah, we should be okay. Right? So this is 5, and this is 4, and this is theta 1. Like that's the situation. So R is the hypotenuse from the coordinate 5, 4 to the coordinate 0, 0. It right, it's the hypotenuse of a right triangle whose legs are 5 and 4. So that's E1, that's the size. That's how hard Q1 is pushing onto the origin. It's how hard Q1 is pushing overall. But now I want to get its X and Y components. Well, what? So I need to multiply that. But, sorry. It was from the diagram. Yes, this thing. Sorry. And I know yes. It was from someone's asking in the direct chat. That triangle that I just drew, I just took it from the diagram, from the original problem. Yes, absolutely. And I'm trying to keep these pages in order. In fact, yeah. So that the answer is yes. I'm going to, what's confused? I know what I'm going to do. One second. Just, okay. So yes, this diagram right here is from is literally, that's just a zoom in on E1 from the original diagram. That's correct. So I've got to multiply E1 by the cosine and by the sine. So you might of theta 1. You might ask, what's theta 1? I don't know. I could figure it out, but I actually don't need to. I can just cut to the chase and say cosine of theta 1 must be the adjacent of 1 over the hypotenuse of 1. The adjacent, if you look at this diagram, is 5. And the hypotenuse is the square root of 5 squared plus 4 squared. Right? The hypotenuse, in other words, is R, is what we mean by R. R is the distance from Q1 to the origin. So what's in the denominator here is R squared. Yeah, what's in the denominator here is r squared. And what is here is the square root of that, which is r. I.e., what I'm saying is E1x must be 9 times 10 to the ninth times 5 all over all over 41 times 5 over the square root of 41. And in what units? If you look at the units, these meters squared canceled out with those meters squared, and this coulomb squared, one of it canceled out with this coulombs. So the units we get at the end are newtons per coulomb, right? So this is E1x. I'm saying E1x is K times Q1, these are all magnitudes. K times Q1 over R squared times X over R. Does any, so I'm saying E1x equals approximately 8.59 times 10 to the 8th newtons per coulomb. Now that's its size. I'm not looking at it. The directions already taken into account in the pictures, but its size is about 8.59 times 10 to the 8th newtons per coulomb. That's E1x. What does that mean in English? It means that is how hard Q1, that is how hard Q1 is pushing on the origin to the left, to the west. It's just a horizontal component of the E1. It's if you were a 1 coulomb of positive test charge sitting at the origin, you and E and Q1 was the only thing that existed, you'd be pushed to the west. You'd be pushed to the west that many newtons. That's the E1x. I'm now going to go on to E1y. E1y must equal E1 sine theta 1. So that means all the same numbers again. It means again, so I'm leaving out the units now because now you see how the units work. So the same universal constant times that same magnitude of charge, which is 5, over the same r squared, which is 41, times, now the only difference now is it's opposite over opposite over hypotenuse rather than adjacent over hypotenuse. So it's now 4 times the square root of 41. That's the only difference in this one. Right? So I do those. So it's going to be 80% of the other one. Yeah. So it's going to be like 80% of the other. So we get, so E1y in magnitude is approximately 1.58 times 10 to the 8 newtons per kilogram, per coulomb. So we got 10 minutes left. So we've got how hard Q1 is pushing to the west onto the origin. We've got how hard Q1 is pushing to the south onto the origin. Now we shift our attention and we look at Q2. E2 goes the other way. E2 is a smaller vector that goes northeast. So it's something like this. So it goes some amount east and some amount north So E2 looks like this. So this is E2x, and this is E2y, and this is theta 2, right? So I'm zooming in on that, turning the page and saying, okay, and this is what you're doing for the homework, obviously. I mean, you want to explain it, make sure you understand it, but you'll have time to sit and think about it because anyway. Um, so E1, excuse me, E2x, what is that? Well, I'm plugging in the numbers. It's going to be same thing as before, like 9 times 10 to the ninth times now the charge from E2, i.e. the charge magnitude of Q2. So it's the other charge we're looking at now. We're looking at the other charge now, that at a magnitude of 2 rather than 5, right? And notice, please, pro tip, if you're still with me, this is a thick computation, obviously, and we only have to do it once, but we have to do it once. I mean, this whole thing we only have to do once. Notice that 2 in the original problem, it like has a negative sign in it. It's electrons, not protons. Absolutely correct. Absolutely relevant. But we've taken that into account already by saying that this arrow is a pull, not a push. And now I'm just crunching magnitude. So I'm not going to double, I don't want to double count that negative sign. Like a negative times a negative makes a positive. So I've already taken into account direction. Here I'm just crunching magnitude, so I just put in 2 there. That's like on purpose. You might want to make a note of that. Over r squared, right? So what then that r2 squared now? I guess I should. All right, I'll put the letters just so you can see. Sorry, I'm not. That's not wrong. That's all right. But I'm just saying, like, in other words, I'm doing this. Right. This is what I'm doing. Right. So, okay. So 8. So 9 times 10 to the ninth times the magnitude of 2 all, and this is R2 now. So what's R2? It is now like 10 squared plus 3 squared, 109, but all multiplied by the cosine of angle 2. So the adjacent from 2 over the hypotenuse of 2. What is that? The adjacent would be 10 now over the square root of, right? It's the same pattern as before. So like 1. And what you get, I'm just showing how you think it through. So what you get is like 6.87 times 10 to the eighth newtons per coulomb. I'm looking at time, we have 6 minutes left, right? So now we've got, that's the third of 4 components that we need. Then E2y, same deal, cut to the chase, 9 times 10 to the ninth times 2 all over 109 times now the opposite over the hypotenuse. So 3 over the square root of 109. And when you do all that out, you get like 4.75 times 10 to the 7th newtons per coulomb. Notice these numbers, these results for the second vector for E2 are a lot smaller in magnitude than the results from E1 as predicted by us and the direct chat person. Like, this is a smaller number because Q2 is a smaller magnitude and it's farther away. What do we do with these results? So now we have 4 results. We now have funny time to leave. Like, we're about to get the answer, but okay. I would stay, but and we have 5 minutes, and that would be sufficient. We now have E1x, E1y, E2x, E2y. What do we do? Add the corresponding components. We're adding them up now. We're getting the combined effect of these two charges. So we literally, just like in physics 203, or with displacements or velocities or whatever, we tally up all of the independent x contributions, and we tally up all the independent y contributions. We're literally adding. We are literally adding each, but we're only adding x to x and y to y, just like when you walk in New York City, avenues add to avenues and blocks add to blocks. So we put the numbers in, and we're almost done. We put the numbers in. But the one thing is, one thing to be very careful now, we're about to add. We're going to add no matter what. But now I step back and I look at my arrowheads. And I don't turn the page because we only have 3 minutes. I look at the arrowheads. If you notice, E1 was pointing south and west. So E1, these components were pointing in the negative direction. E2, they were pointing north and east. So they don't get so I put my negative signs in now before I actually do the addition. And I base those negative signs. So I'm doing addition no matter what, but some of the numbers are negative. So I put the negative signs in and I get results. And the results I get, nor are we done, are negative. So what do I do with these two results? We have 2 minutes. We have seeming two results. Well, that's the X component of the final answer and the Y component of the final answer. So I make one big triangle. I go, oh, at the end of the day, the field is pushing to the left because negative, to the west, with an amount of like 7.01 times 10 to the 8 newtons per coulomb. And from its tip, I always draw horizontals first. I draw a vector that's almost as long, but not quite as long. A vector that's like 6.40 times 10 to the 8 newtons per coulomb. And the answer that I'm looking for, oh my God. Sorry. That has to point down south from the original. I totally said it right and then just did it wrong. The original vector goes to the west, and from it, a vector goes down to the south. And so the final answer that I'm looking for is, as predicted, a vector that goes to the southwest. The final answer has to be the square root of 7.01 times 10 to the 8th squared plus 6.40 times 10 to the 8th squared. So the final answer E will be approximately 9.49 times 10 to the 8th newtons per coulomb at an angle of what? Of the arc tan of 6.40 over 7.01. In other words, approximately 42.3 degrees southwest. This is my final answer, is these two pieces of information. The magnitude of the field is like 900 billion newtons per coulomb. And the direction of the field is 42.3 degrees southwest. So there's an arrow sitting at the origin, shoving down southwest. It's the combined effect of Q1 and Q2. So every one positive unit of charge that could be found at the origin will be pushed that hard. If there was 2 units of charge, they'd be pulled, both of them, each of them would be pushed that hard. So there'd be a total force of like 18 or 19 times 8 newtons per coulomb. That's how it works. That's the answer. You've been very patient. Okay. I'll see you in 2 days. I'll see you in 2 days. And I'll hang out for a second if there's any questions. But good job, everybody. That's the whole. Have a good one. Thank you. Have a good one. Okay, I'm turning off the recording. Have a nice day. Awesome. Okay, I'm turning off the recording.